But this is Project 2. I'm Anthony.
My name is Greta,
And my name is Laura.
and we are Project 2 working on parameterizing turbulent flow and the planetary boundary layer.
So we have an overarching goal that we'll use as an outline throughout our presentation. It's to use the equation discovery methods to develop accurate and interpretable parameterizations for vertical turbulent fluxes in the planetary boundary layer. Um, and we'll first start off with vertical turbulent fluxes and exploring the planetary boundary layer.
Okay, so just to provide some background information before we kind of dive in, what is the planetary boundary layer? Well, it's something we're all really familiar with because it's basically where we live on Earth. So the planetary boundary layer is the lowest level of the troposphere. It's about 1 kilometer thick, and it's where we live our day-to-day lives. But something important to note is that it's really influenced by the Earth. The heating and cooling of the Earth kind of influence all the parameters that are going on in this. So as during the day, as the Earth heats up, it makes the air warmer. They start to rise, have more buoyancy and such, and the planetary boundary layer actually grows. At night, when the Earth is cooler, the planetary boundary layer is then going to shrink, fall a little bit. Um, so it is directly affected by our surface heating and cooling, but because we are still in this 1 kilometer area, it's a little bit too small to be picked up by climate models, which typically are on scales of around 100 kilometers, and we're dealing with like a smaller area. And just because as the Earth heats up different areas, it creates these small scale eddies and things that move up. So this vertical turbulent flux, as it brings up, it can transport things in the air. So pollution, moisture, heat, that all gets kind of moved on up as these air particles start to rise and work their way up. So this is called a vertical turbulent flux. So if you're ever on an airplane at any point, when the plane starts to kind of shake before you land, that's kind of this turbulence, just this movement of air. Something else I just want to mention before we move on is that the planetary boundary layer is actually capped a little bit. So we reach this place as we move up, we reach a temperature inversion, which we can kind of see where this capping of the smog is. At that point, it's where then actually as we move up, then the temperature does start to increase as we go up. Whereas before that, as we move up, the temperature starts to decrease. And at this capping inversion, air can get incorporated into the planetary boundary layer in a process through entrainment, but we'll talk about that a little more later.
So if you want to study the PBL, it's good to have a lot of data. And if you want to have a lot of data, it is good to simulate it. And so we use large eddy simulations as our data. We also want a good amount of variance in our conditions. And so we switch them around. We change the horizontal wind, the surface heating, and the inversion strength. And these will be important later in the presentation. This data captures the evolution of the PBL at a very high resolution. So in the X, Y, and Z plane, we have a resolution of 24 by 24 by 6 meters, which is a sharp contrast from today's climate models. We're also going over 2 hours minute by minute. Now, this is a really cool picture of what we're working with here, and it is a picture of vertical velocity. It's a two-dimensional slice of this simulation. And so these bright yellow spots are upward and positive vertical velocity, and these dark blue spots are negative, so downward vertical velocity. But we can't capture all of this information, and it's far too noisy and diverse for the methods that we're going to use. So in order to deal with this, we coarse grain our data and we average it down to a vertical profile, which is that black line right there. So now the dimensions that we're working with are the height in the planetary boundary layer and the time evolution. But we still get a ton of variables, and we get to investigate their higher order moments. In order to achieve our goal, we want to use equation discovery methods, and the specific method that we use is called symbolic regression, which is somewhat a cross between absolute magic and the way that somebody would discover an equation if they had no idea what was going on in the field, right? What it does at the end of the day is it produces human interpretable equations. A good example of that is a linear regression. 4 times humidity might mean something to a scientist. A bad example of that is a neural net. You put inputs into something, it's an absolute black box method. It might have really high predictive power, but you have no idea how it gets to its output. So the core of symbolic regression is essentially a genetic algorithm inspired by evolution and an optimization task. It takes in operators like the plus sign and the minus sign, basic functions like trig functions and e to the x, and coefficients, and it optimizes equations. So what you do is you put in an input, multiple inputs. You'll be putting in your response variable, your target, the thing that you want to get, and a number of potential predictor variables which you believe could constitute some form of equation for it. Now, what it's going to do is it's going to create candidate equations and compare them. So it's going to start with something very basic, say x, and then it'll make two candidates, x plus y and xy. And then it'll staple coefficients onto them, optimize them to see which one fits better to the data, and pick the better one. And it'll continue to evolve off of that, kind of randomly searching through the equation space until you get something that works. And so your output is going to be a physical equation that relates the predictors and the response. I've got the predictors in pink here and the response in blue here because when we look at ugly equations later, I want them to be in those colors. Something that's very important to mention is that this algorithm has a lot of randomness in it. And so when you're optimizing, you're going over a non-convex loss function. There's absolutely no guarantee that this is going to converge. And in real terms, this means that there's absolutely no guarantee that we're going to find the right equation.
The next part of our goal is to use accurate and interpretable parameterizations.
So the first thing we wanted to model in the boundary layer is entrainment velocity, and that basically answers the question, how does the PBL grow over time? Greta earlier mentioned this capping inversion. So it's in this graphic, it's C, and for our case, we use H as the height of the boundary layer, and over time, it'll grow and it'll shrink with the Earth heating and cooling. Um, an important thing to note is that the capping inversion isn't like a strict lid on the boundary layer. It's a little bit like fluid. So air will rise up when it's heated and it'll overshoot the boundary layer a little bit. It'll mix in air from the free troposphere, which is this area, and then it'll go back down. And that's how the height of the boundary layer changes. Um, in our case, we represented by DHDT or WE. DHDT is just the time evolution of the boundary layer, but it usually includes more large scale components. But in the case of our LES, we don't have those large scale components. So we just say that entrainment velocity is WE. And so the equation that we wanted to discover or rediscover is this top one over here, DHDT equals A, which based off of theory is like around 0.2, and based off of observational data is closer to like 0.4, 0.43, times a bunch of this G and this theta naught, which is a bunch of constants, times this ratio. The numerator is the buoyancy flux at the surface, and the bottom is the change in potential temperature in the inversion layer. To run our equation discovery model, we inputted this ratio as its own variable, as well as this UG, which is imposed horizontal wind throughout our simulation, surface heating, and the change in potential temperature in the free troposphere over time. And we see that our equation discovery model had this negative 10.751, which roughly translates when we like take the G and the theta naught into consideration, roughly translates to an A of 0.35. Times the ratio that we wanted minus this extra term. And this extra term is some constant times the imposed horizontal wind. And we think that that implies that the horizontal wind has something to do with mixing in the boundary layer. And that's also something that modifies the height of the boundary layer over time.
Okay, so the second equation we kind of wanted to look at was in the inversion layer, this mass flux. So as entrainment is kind of happening, how particles are moving between the boundary layer and then kind of the free atmosphere. And we kind of wanted to look at this because there are some discrepancies in the way we can calculate entrainment, our entrainment velocity. Some textbooks say that this W theta H minus, which is vertical turbulent heat at the top of the mixed layer, is equal to our WE, our entrainment velocity, times the change in temperature in the inversion layer. And so we wanted to use Laura's equation as our new WE to see if this still held true, because we are able to calculate this W theta H minus from other variables in our equation. We're able to pull everything else and calculate it as a residual. And then we were looking to see if we would get this like plus overshoot term to see if there was some other dependency for this mass flux. However, we did kind of run into some maybe limitations with equation discovery here. we kind of found that equation discovery does tend to struggle to adhere to some of our laws of physics. And while it does have built-in measures to respecting units, we were getting some different scales on our various equations we were coming up with. So we did choose to not include the final equation that we potentially found just because there felt like there was too much variation if it could actually be concrete. But there definitely was some other term in this overshoot, so not entirely sure what it is, but that is what we have.
The final equation that we were interested in rediscovering and improving upon was something to do with the heat flux. And so we're particularly interested in the turbulent component of warm air because it vertically transports important things like pollution or humidity. And so the way that this is done, we want to study this W theta right here. W is the upwards component, theta is the heat. The bar above them indicates a covariance, and that's how we get upwards heat flux. So what we'd like to do is there's this parametrization for this P term. This P term is a pressure redistribution term, which acts as a source or a sink for that term. So essentially what we're doing here is we have this equation. This is our response in blue. And then we have some constants multiplied by these 4 key pink predictors right here. And then after that, we get the resulting coefficients and plug them into a parametrization for the heat flux that's dependent on them. Now, the simple goal here is take this ugly equation, take this response, these 4 predictors right here, a couple others, toss them into the symbolic regression software, and see if you actually get the same functional form for P, if you get the same constant times variable plus constant times variable, and so on. If we do actually manage to recover the functional form, we want to compare the discovered coefficients to theoretical estimates. Weirdly enough, I mean, coefficients are almost always data dependent, but in a lot of the papers that I looked at, they were like, these are the typical values for coefficients, which we're surprised by. So we'd like to see if we have any discrepancy. And then after that, we'd like to plug those resulting coefficients into our parametrization and see how well it does. So first things first, I thought this was a funny figure to put up here because the true vertical profile of the P term is in black here. And then all of these other lines are completely nonsensical, overcomplicated equations, which are really close to what we want and are essentially one of the negatives of using symbolic regression. Now, when we finally do recover the true functional form, it is in the form that we want. And it's this green line right here, which is essentially sitting on top of the black line and indicates a really, really good fit if you look at the predicted versus actual plot. I don't know if that's too small to see, but we have an R squared of 0.98, which is so high that sometimes it's unbelievable. But the interesting part here is that the coefficients that we get for our functional form differ very strongly from the theoretical or typical values. In fact, if we are to plug in the theoretical or typical values, we would get this blue line right here, which is very far off from the black, which is our ground truth, so to speak. So that's an interesting discrepancy. Now, everything is going well. We have the functional form, we have the coefficients. Let's see how it does in the actual parametrization. And the short answer is really poorly. This black line is once again our truth. This green line is our discovered coefficients plugged into the parametrization. And luckily, we're doing better than theory because theory is in blue. But this discrepancy is most likely from 2 things. Number one, not to get into the specifics, but in our data, we calculate a variable in kind of a funky way, and it's shaped very similarly to the profile of our lines. So we suspect that that might be messing this up. And then secondly, we suspect there are also extra dependencies on large-scale forcings. Now, I showed you guys that picture with all of those semi-transparent lines earlier to show that symbolic regression had a really difficult time picking up the original functional form. So what we did is instead of trying to get it to rediscover novel dependencies, we just did it on the coefficients. We used the functional form, we took the coefficients, and then we plugged in the coefficients as a response and large-scale forcings like horizontal wind and surface heating into their own symbolic regression. And we get a lot of nonsense, but really, really frequently, the first coefficient is dependent on the horizontal wind. Now, this may be so technical that it's boring, but this first term right here represents the return to isotropy term of the equation. This means that eventually everything mixes around in the PBL and there's a semi-homogeneous state going on. Now, I know we're talking about vertical things here, but we suspect that the horizontal wind likely contributes a lot to the mixing, once again. And so that's a dependency that actually makes sense and should be explored more.
So just to kind of wrap up just what we've done with this project, we were able to have basically two successful rediscovery for equations, our WE, our entrainment flux, and then the P, the pressure term. And both of them really did point to this extra dependency on large scale forcings, which is our horizontal wind. Additionally, we were able to make a GitHub repository. So this work can be reproduced. All of our code is accessible, and just by changing the folder path, people can potentially re-go in and use this code and continue it on for further work. So the future directions potentially we'd like to look more into are just like including more simulations with varying initial conditions. Also, refining the second stage of symbolic regression for finding coefficient dependence on large scale forcings, and just building in more physical and consideration of units. One of the big limitations of equation discovery is relying on this local information, but we'd like to probably bring in some non-locality space. All right, and thank you.
Okay, we have time for two quick questions. I see one in the back.
Great work. I have a comment, one of the questions. Sorry about that. But have you looked into work about symbolic regression that uses dimensional equivariance? There's two papers that I can think of. One is by Steve Brunson and folks at UW, and the other is by people at Soledad Villar at Johns Hopkins. What they do is they specifically construct dimensionless groups. So using something called the Buckley-Pi theorem, which sort of like encodes this units into the equations because you want the units on the left, units on the right. And their codes are, I think, publicly available. So I don't know if you have time this summer, that would be something look into, unless you've already looked at it and you still not converge to the next.
Is one of these papers the PySR software? Because I don't believe I'm familiar with them.
No, I think it's
We can absolutely, yeah.
But PySR, well, I think PySR can be built on top of these papers too. It's just how you sort of what quantities you put in is what quantities you get at the other end.
Oh, I see. That's yeah. I'd love to look at those papers.
It's part of not the non-locality, which I think is also a big issue.
PySR can fix part of the problem as well. It can reject like candidate equations if they don't adhere to certain unit constrictions, and it can also it has like a feature for respecting the units. It's just that the feature works really strangely, and we found it rather unhelpful. But in theory, it should be able to fix part of the problem. But yes, absolutely. Please Slack me papers.
I wanted to see if I understand, is the horizontal wind term, is that not in the theory-derived parameterization, but popping up in your equation discovery?
Yes. So when we do this equation discovery, we put in all of the terms that are derived in theory, and then we toss in a couple extra. The easiest ones to toss in are the large scale forcings because they're simple. But usually it's physical expert knowledge which guides us as to which parameters to toss in, and large scale forcing was just something that was not in there previously.
Would this be an easy way to improve the theory-derived parameterization?
That's the suspicion.
That's
Yeah,
awesome.
is that a lot of these initial conditions aren't being given the consideration that they should.
Okay, thank you so much to all of our presenters.
Thank you guys.